Howdy, AP PreCal, it's Ms. Kosh. I am working through Mr. Passwater's multiple choice questions on Unit 2, and they're tricky. So I kind of stumbled all the way through the last video, so sorry, but I'm just as human as you are. Anyway, whatever. Okay, let's keep going. I don't know, is this video 5? The graph of the piecewise defined function is shown above and consists of 3 line segments. What is the value of, so this is saying f to the -1 of 3 is saying like f of x would equal 3. So I want a y value of 3. And when I do, I get an x value of -4. So there's my answer. That was good. Okay, so now they're telling us g of h is equal to 2 times, what am I saying? H of x is equal to 2 times g of x plus 3. If the point, this 3, -2 is on the graph of g. Okay, so what this is saying is g of 3 is equal to -2. Well, so what do we know? We know h of, the only thing we know, we can say h of 3 would be equal to 2 times g of 3 plus 3. G of 3 we know to be -2, so this is 2 times -2 plus 3 is -4 plus 3 is -1. Which of the following points is on the graph of the inverse? Okay, so what we just found is that we have h of 3 is equal to -1, which means that h has the point 3, -1, which means the inverse would have -1, 3 as a point. Oh, that was clever. That was a little tricky. Okay, the inverse. So, oh, these are fun. One way to think about this is this has an, the domain restriction is that x can't equal -4. And the range, okay, so, or we have an asymptote of x equals -4, and then when we divide, this is the same degree, top and bottom, so we divide the leading coefficients. So we have an asymptote when y equals 2, and so what is going to happen is we're going to have x minus 2 on the bottom, and then we're going to have a leading coefficient of -4x, and then probably something here. So if I just look at that, okay, these two I can eliminate immediately because they don't have that x. So basically, I had an asymptote of x equals -4, which means that the inverse is going to have an asymptote of y equals -4, which means I can divide and have this and get -4 over 1. And then this original one had an asymptote of y equals 2, which means that my inverse is going to have an asymptote of x equals 2. So I've narrowed it down to these two. But you know what, just for the fun of it, maybe we should switch x and y and solve. So x is equal to 2y. If you didn't like the way I thought through that, I'm pretty confident that C is the answer. But let's just see, what would we do if we wanted to do something else? Okay, so this is x times y plus 4 is equal to 2y minus 3. Let's get my y's on one side, so I have an xy, I have a 4x. I'm going to move this over. 2y is equal to -3 minus 4x. And so if I factor out the y, I have x minus 2. So I end up getting a -4x, here, let me write it down, minus 3. So it's a -4x minus 3 divided by an x minus 2. Oh, I was right. Okay. Which of the following statements is true about the construction of, okay, if this is g, what is, so what did this do? This has an asymptote. It took my log function, which normally has an asymptote at x equals 0, and it shifted it to the right 4. So the domain of this guy is going to be from +4 to infinity. So the range of the inverse is going to be from 4 to infinity. Okay, let's see. The inverse cannot be constructed. Yes, it can. The inverse is exponential. The inverse of g can be constructed, and the graph of g has a domain of all real numbers. Yep, because the range of this guy is all real numbers. The inverse can be constructed, and the graph of the inverse has a domain. No, it's got a range of y is greater than 4. The inverse can be constructed. Yes, we think so. And the graph of the inverse has a range of real values. No. Okay, so another way to think through this one. So what did I say? It has a domain of that. The range. One way to do this is to say, okay, x is equal to log base 3 of y minus 4. I can do I heart logs. 3 to the x equals that. 3 to the x is equal to y minus 4. So my y value is equal to 3 to the x plus 4. So what did this do? It took my exponential function, exponential growth function, and it moved it up 4. So it's got a domain of all reals, but not a range of all reals. Okay. Oh, logs. I like logs. I get tired of logs. I don't mind them, but by the end of the unit, I'm like, are we done yet? But that's what happens when you do it too many times. Okay, so here we go. What is the value of f of 2? Oh, here we go. So one way to think of this one, I'm going to change it up a little bit. Now I'll do it twice for you. This is log base 8 of 2. So what I see is I can use a change of base property, and I can say log base 2 of 2 over log base 2 of 8. Well, this is 1 and this is 3, so the answer is 1/3. If you didn't know what happened, hold tight. On this, or I could say, okay, log base 8 of 2 is equal to some value k. K is our favorite letter. 8 to the k is equal to 2. Well, 8 is 2 cubed. So this becomes 2 to the 3k is equal to 2 to the 1. 3k equals 1, k equals 1/3. And that's how we get, that's another way we get 1/3. What's the value? Plug in 1/9. Oh, and -2. Because 9 is 3 squared, but it's on the denominator and it needs to be in the numerator, so it's a -2. So 1/9 was equal to 3 to the -2. If this is a struggle for you, go back and watch all my log videos, because this should be pretty foundational. That sounds terrible, but it's true. Okay, what input value yields an output value? Okay, so we have log base 4 of x equals 1/2. This is where we used to do the I heart logs. This to this equals that. So 4 to the 1/2, so basically the square root of 4 is 2. There we go. For which values will they intersect? Oh, okay. Log base 10 of x, we don't have to write the 10, is equal to 1. So 10 to the 1, x equals 10. Is that right? Function r is... So this is just saying, oh yeah, okay. Here's our logarithmic function, does something like this. It grows, but slowly. This is the point 1, 0. And then when does it hit 1? Well, it hits 1 at 10, because log base 10 of 10 is 1. And so here's this line y equals 1, and it hit there at 10. Okay. The function is log base 4 of x. Which of the following is about the inverse is true? So if I said x equals log base 4 of y, this is 4 to the x is equal to y. The inverse is 4 to the x. And 4 to the x is defined for all real values. I think that's the right one, but I'm getting a little cross-eyed again. This has a unlimited, like the log function has a restricted domain. The exponential function does not have a restricted domain, but it has a restricted range. We did that side. Okay, how are we doing? So we've got these are on the graph of an exponential function given by this. Okay. Okay, so this h is, and so they're telling us, oh, these are inverse functions. Okay, so if you have -3 1/8 as a point in the exponential function, you'll have 1/8 -3 as a point here. Yeah, can I just assume this? -1/3, where'd they get that mess? I mean, that's clever, I guess. But the point is not on the graph. No, I think this is the correct answer. Let's just make sure. If I have x is equal to b to the y, I can change this to logarithmic form by saying the base this to the, b to the y is equal to x, and I double check and I'm back to where I started. So do they give us the 2? Yeah, those are inverse functions. And so whatever, we can switch the x and y's and we're good to go. The table shows values of a function at selected values here. Which of the following claim and best fits the data? Okay, so what do I see? I see that the x values are being multiplied by 1/2 and the y values are being added by 2. Okay, so the input has a common ratio, the output has a common difference, is how I like to think of that. Which of those? Okay, it's best modeled by, when the input has a common ratio, it's logarithmic. So it's not exponential, it's going to be logarithmic. Because the input values change proportionally. Okay, common ratio change proportionally. Output values equal length intervals. Yeah. Output values change proportionally as input values increase at equal length intervals. Wait. Oh, it's a log because the input changed proportionally, not the output. Okay, the output didn't change. Okay, so it's C. Those are like so many details. You just have to read closely and make sure you're catching the differences. This is kind of the same idea. I don't feel like doing it. So is that. Okay, let's jump down to this one. Which of the following statement is, I mean, this might be different, but I'm fine. You're fine, you'll be fine. Which of the following statement about f is true? Well, so this had the log functions look something like this. This vertical stretch will pull it farther apart, but it doesn't change its domain and it doesn't change its concavity. It's increasing and concave down. Okay. What's happening here? Well, now I took my log graph that would have looked like this and I flipped it over. So it's decreasing and concave up. Okay, what happened here? Well, I might rewrite this one as -2 log base 6 of x plus 3. So what does this do? It would have looked like this, but the negative does this to me, and then it moves it up. So it's going to be kind of something like that. So it's decreasing and concave. I mean, basically we had a point. If I look at this graph, y is equal to -2 log base 6 of x. I'm looking something like this going through the point 1, 0. Because if I take the log of 1, I get 0 and then whatever. So now all I've done is I've moved this point up 3. So that was what I was trying to show here, that moved up 3. What did I just say? That was decreasing and concave up? Okay. Yeah, I'm getting through some of these. I don't know that I'm going to finish today. We'll do a few more and then call it a day. Okay, what does this graph do? It grows, but it grows a little slower than it would have otherwise. So as I go to positive infinity, it approaches, no, it doesn't approach 0. It approaches infinity. It goes there slowly, but it goes there. Not negative infinity. This is saying as I go to 0 from the right, I'm actually going to negative infinity. So this is the best answer. This one would have been your log function, but it's flipped over, so it's doing something like, well, ish. So as I go to infinity, I approach 0. Nope. Infinity, infinity, nope. Infinity, negative infinity, yes. 0 from the right, negative infinity, nope. It goes to positive infinity. Okay. Logarithmic function, what did this do? It was the same idea we saw a second ago. It flipped over and then shifted up, but it's kind of hard to see what that. As the input values increase without bound, the output values increase without bound. No, the output values, it's going to look roughly like this. So as they increase, then they're going to decrease. They don't get close to 0. They don't increase, they don't get close to 0. So as it gets arbitrarily close to 0, they decrease. No, they increase because they're going up this way. Okay, see, knowing what these parent functions look like can make a huge difference. This graph is going to look something like this. As the input values increase without bound, the output values decrease. Nope. They get arbitrarily close to 0. Nope. They increase slowly, but they increase to 0. As the input values decrease arbitrarily close to 0, the output values decrease without bound. Yes. They don't increase without bound. That would be going that way. Okay, let's see. What's this one? I think this may be my last one for today. Output values increase without bound. Output values go up without bound as the input values increase without bound. And the output values decrease without bound as the input values get arbitrarily close to 0. I think it's this one. Well, this is not, the input values are going to negative infinity. The output values here are approaching 0. But they're saying they want the input values to get to 0. I think we're looking at this guy. Let's verify. What did the first part say? The output values increase as the input values increase. As the input values increase, the output values were decreasing, so that's no good. As the input values increase, the output values were increasing. So this fits the first part, but not the second, is how I see it. Input was increasing, output was increasing. Input was increasing, output was decreasing. That's no good. And so let's check this last part one more time. The output values decrease without bound as the input values get close to 0. Okay, yeah, it's definitely that one. All right, well, I have more to do for this unit and for unit 3, but that's all she wrote for today. Hopefully that was helpful. Like, subscribe, comment down below. Let me know how I can help you. I'll see you in the next one.